So hopefully you've already watched the videos on Taylor polynomials. Now we're switching gears to something very similar, but they're called Taylor series. Because if we change this into a series, we can make it an infinitely long polynomial. And at the point that we make it an infinitely long polynomial, we can then be exactly accurate by using a polynomial to define another function such as e to the x or sine of x or cosine of x. So here you see the polynomial written up top. So hopefully you can see how there's a common thread here between the general term of the polynomial, sorry that's so small, and then what you plug in to the function there. Okay, so that is how the series would be written. We have basically the same pattern where you've got a derivative on top. Whatever derivative you're doing, you do that factorial on the bottom, and then you do x minus c raised to that power. So that's how the Taylor series works. Now the main thing we're going to be doing with Taylor series is taking some common Taylor series and using them to find other series. So here's what I mean. These are 4 examples of Taylor series that you should memorize. They're worth memorizing, they are common, and it'd be good for you to do. So we have 1 over 1 plus x, e to the x, sine of x, and cosine of x. So these 4 are very important, and the idea is, for example, if you have e to the 2x, rather than having to do the whole long process we had to do with polynomials, you can instead do just a little bit of tweaking to this e to the x function, and you can get e to the 2x from it. So let me give you an example so you know what I'm referring to. If you want, you may want to pause here and write these down. So first example, write the Taylor series for sine of x squared. Now what I've already done here is I went ahead and wrote down sine of x, because obviously if we're going to be able to build sine of x squared, we're going to have to do it by starting with sine of x. So my next step then is to figure out how I go from sine of x to sine of x squared. Now if you think carefully about that, you should be able to see that what we're really doing is substituting. We're replacing. We have replaced the x with x squared. So that's all you have to do with the right side as well. You replace every x you see with x squared. Okay, and just for general purposes, we'll plan on doing the first 3 terms and also the general term. So don't leave it like this. Go ahead and simplify your exponents, and you'll have x squared minus x to the 6th over 3 factorial plus x to the 10th over 5 factorial, and then the general term would turn into x to the 4n plus 2 over 2n plus 1 factorial. And that would be your answer. So you see how by using a Taylor series that's already known, we can just do some tweaking, some exchanging or changing, and we can have a completely different Taylor series that was much simpler to come by than it is the way we do it with Taylor polynomials. Now one thing I will point out, because you may be wondering, well, why did we have to do all that work for Taylor polynomials? A few reasons. One is it's good to understand where these things come from, but the second is, if you notice, all 4 of these are centered at 0. So this works great if it's a Maclaurin series, if they're centered at 0. If they're not centered at 0, you still got to do the long way. So keep that in mind as well. So second example, write the Taylor series for cosine of the square root of x. So I went ahead and wrote cosine of x for you. Again, I'm just pulling that from the known ones you should just have memorized from here on out. And I'm going to replace the x with the square root of x, because that's what happened. You substituted square root of x in for x. So I'm going to replace every x I see with the square root of x. Okay, one thing I will point out, if you notice right here, in the original I had a minus there and then I put a plus. It doesn't matter a whole lot whether you put minus or plus right there. The reason I put minus in the first one is the next term is going to be subtracted, so that's completely fine to do that. And in fact, that's the only time you should ever put minus, is if the next term is going to be subtracted. You can see that cosine is alternating. It goes from negative to positive, negative to positive. But if you keep in mind that you can accomplish subtraction by just adding a negative, that's why it's okay to put a positive here even if you're subtracting the next one. So that's something I certainly won't be picky on, and I'm fairly certain it is not correct or incorrect either way. Again, assuming if you know the next term is positive, you should always put positive. If it's negative, it can pretty much go either way. So now let's go ahead and simplify what I've written. 1 minus, and it'll be x over 2 factorial plus x squared over 4 factorial. And then this will become x to the n over 2n factorial. And that's because square root of x is the same as x to the 1/2. 1/2 times 2n is just n. One other thing, when you're writing these, they are series, so you should always on the end have a plus ... to imply that it keeps on going and going and going. Third example, find the Taylor series for 2x times e to the 3x. So you can see that this one has two things happening. And so since there's two things happening, we're going to do it in 2 steps. First, we've got to deal with the 3x up here, and then second, we'll deal with the 2x out here. I would always deal with the substituting part first, because we are replacing x with 3x. So everywhere I see an x, I'll replace it with 3x. Now, I go back through and simplify that, and I get 3x plus, and this is why I always put these things in parentheses. Anytime you're substituting, it's a good habit to put them in parentheses, because you've got to do 3 squared, so that's 9x squared over 2 factorial. In this term, the general term, you can be kind of flexible on how you write it. You can leave it just as it is, or you could write it this way. Both would be fine, so you can just go with your preference on that. Okay, but we're not done, because it didn't ask for just e to the 3x, it asked for 2x times e to the 3x. So to go from e to the 3x to 2x e to the 3x, we're not substituting anything, we haven't replaced anything, we're just multiplying. So just like we were multiplying 2x times e to the 3x, we need to multiply 2x times every single one of these terms. So 2x times 1 plus 2x times 3x plus 2x times 9x squared over 2 factorial plus 2x times 3x to the n over n factorial, and so on. So if we simplify that, we get 2x plus 6x squared plus 18x cubed over 2 factorial plus, and then here, again, you can be kind of flexible. I would probably be inclined to write it as 2 times 3 to the n times x to the n plus 1 over n factorial. That's probably the best way to write it, but it's not incorrect even the way it's written originally. So the general term you can be a little more flexible on when it comes to simplifying. But one reason I did this example is to make sure you understand the difference between substituting and multiplying. It's a big difference there. We substituted x for 3x. So notice the 1 did not change because there was no x there, so there was nothing to change because we weren't replacing any x. However, with the 2x, the 1 did change because we were multiplying. We were multiplying 2x times everything, so we had to do 2x times 1. Okay, final example. Find the Taylor series for 3 sine x minus 2 cosine x. Now, I did go ahead and write the general forms here, or the general terms here, but when you're adding and subtracting 2 different functions, that's going to get kind of messy. So I wouldn't worry too much about the general terms when you are subtracting 2 different functions. Now, we have sine of x here, and we want 3 sine of x, because what we're going to have to do is first get 3 sine of x, then get 2 cosine of x, and then we will subtract the 2. So just so you know, I'm going to expand sine a few more terms since I'm not going to do the general form or general term. We'll get 3x minus, sorry about that, 3x cubed over 3 factorial plus 3x to the 5th over 5 factorial minus 3x to the 7th over 7 factorial, and so on. So notice again, since we are multiplying, you just multiply 3 by every term. We're not replacing anything. If we'd had sine of 3x, we'd be replacing every x with 3x, and that would give us 3 cubed and 3 to the 5th, but we're not doing that. We're just multiplying. So now let's do cosine 2 times that. So now what we have to do is subtract these two from each other. 3 sine x minus 2 cosine x. Now I would try to keep these in order, so I'd start with my constants. 0 minus 2 is negative 2. 3x minus no x's is 3x. And then let's see. 0 minus negative 2x squared will be plus 2x squared over 2 factorial. And then negative 3x cubed over 3 factorial minus 0. And then 0 minus 2x to the 4th over 4 factorial, and so on. So with those, I wouldn't worry too much about the general term, just because you really end up with 2, and then it's not so general.